Okay, TAM 210, we're going to finally go over force couples. So force couples are a specific subset of how we can handle moments depending upon the arrangement of the force vectors that are causing the moment. So here I've drawn two force vectors that are equal and opposite to each other and of the same magnitude. So they're both labeled F, but one is acting at A and the other is acting at B. And I've defined here the coordinates of A and B on the right. So again, we can take the sum of the moments about O, the origin, as ROA. Individually, we can calculate the contribution of the moment due to the force acting at A and add it to the contribution of the force acting at B, and then we'll know the total moment, right, at O of this system. So ROA, that's going to be cross minus F plus ROB cross F, right? And there's a property that says if you have a scalar inside the cross product that you can pull it out. So the minus 1 here is our scalar that we pull out. So we can make this minus ROA cross F plus ROB cross F, right? And so now I'm going to draw what those vectors are. So the vector RO to A, right? Actually, we're going to do one more step. So now we can pull out the F, right? There's a property that says that we can pull out if there's a common vector here and here in the cross product, then we can pull that out, and this is going to be ROA plus ROB. So now this is just a vector sum crossed with F. Now I'm going to draw that. So what is minus ROA? That vector, right, is really the same as going from A to O. So I'm going to draw that up here. So that's what this one is. And then ROB, right, is positive already. So we're going to draw that one here to here. And so what does that mean? If we do the vector sum, then we're going to get this vector here, right, tip to tail, or tail to tip. And so then this is equal to R from A to B cross F, right? So now the question is, doesn't matter where we took this with respect to, and in the case of couples, no, right? So that's not the same for just the moment about a point. In the case of force couples, it doesn't matter where we take the moment with respect to, right? So here, now I've drawn a point C, right, and I've labeled its axes here, or its coordinates, and we can do sum of moments with respect to C now. And this, of course, then is the vector from C to A crossed with minus F plus the vector from C to B cross F. And then I'll do the math again. RCA, pull out the minus sign, plus now RCB cross F. And now we can pull out the F. And what you'll see after I do all of this cross F is that we get the exact same vector sum again, right? So RC C to A is still this vector here. And then R C to B, this one, adding those up. What do I have to get? I have to get that exact same vector back again, right? And that's a special, and that's because we're dealing with the force couples. RCB cross F, right? So now you might be thinking, well, another way, before I go further, is you could even take this with respect to A, right? So what a force couple does, right? We can just take the sum of moments here. Since we can take it about any point, in this case, if I take it at A, this one contributes nothing, right, to the moment. It's not going to cause any spin because it's not acting a distance away. It's passing through the center of A. So it's just going to be directly RAB cross F, right? The trick is this is basically, right, a really simple scalar version of that moment vector, right? Because we already have that perpendicular distance, but often you don't have that, but it really doesn't matter in this case, right? So some students were saying, well, why doesn't it matter, right? And let me show you, hopefully mathematically, that that's the case with this last example. So what if I had my force vectors arranged this way? right, where A is defined here, but now I scooched B over a little bit. And so we know that the sum of the moments with A is going to be RAB cross F. But now notice, right, RAB has two components here. It has an X component. Let me do that in my blue. I like to use blue for the position calculations. Is equal to whatever the X component in the B minus the X component in the A. And now I'm going to have RABY is equal to BY minus AY. So now if I do that determinant, I'm going to show you that you're going to get the exact same thing. So moments are in purple. So we're going to do the determinant of RABX, right? RABY. This is just that cross product with respect to F, right? And F in this case, right? I'm taking the moment about A due to this force F, which is acting in the positive X direction, so that's F in 0. And so now, right, you'll see that you get minus RABY times F, which is exactly what you'll get up here, right, that I showed you here. So it really doesn't matter, right, whether these two happen to be, there is no real points here. It's from the origin of one vector to the other, right? The only critical component with the couples is that F have to be equal and opposite, right, in magnitude and directions, but a distance apart. Of course, if they were collinear, then they do nothing and they are not a couple force anymore and do not result in a couple moment. So I hope that helps explain a few of those things. If you have any questions, please come to office hours or let us know. Thanks.